Hi, I'm Cynthia Ionova, and today we'll be talking about automation of creep and stress relaxation experiments with MEMS device. This project was done in collaboration with Dr. Pavan Kalu and Adlai Gakwa. A little bit about myself. I was born and raised in Phoenix, Arizona, and I currently attend the University of Southern California, where I'm studying for my bachelor's and master's in chemical engineering. I will be graduating next May with my bachelor's and the year after that with my master's. So for background on what exactly is a viscoelastic material, they're essentially materials that do not exert constant tension when under stress. So on the left, we have a creep experiment where a shear stress is applied and then the resulting strain is measured. Strain is material deformation from stress. As you can see, the result really depends on what kind of material we have. Elastic material suddenly deforms and, when the stress is released, returns to its original shape. Viscous materials experience a steady rise in the strain that they experience, and viscoelastic tends to be in between with a sudden deformation that tapers off over time. The opposite is experienced in a strain experiment, with the viscoelastic material experiencing a spike and then an exponential decay in the stress. Stress and strain experiments are usually done with a microelectromechanical system known as MEMS based tensile test platforms. In these, as shown in the image on the right, the material in question is placed in the middle and then it undergoes the stress or strain. However, studying viscoelastic materials then poses a few challenges. Constant stress, i.e. creep experiments, would require active feedback loop-driven control systems. The OREU group is achieving this feedback manually, which resulted in long rise times in the order of tens of seconds, and an inability to study the time dependence of the material at these timescales. Moreover, long duration experiments and jumps in stress or strain due to temperature changes have been unavoidable. Which brings us to my project. This O-REU project will focus on developing LabVIEW-based codes to automate the experiments that this group runs. Specifically, we will be detecting the edges of the device and tracking its movement. So to start this project off, I did a literature review for MEMS-based testing that can be automated. However, there was no research done specifically on that, but I did learn more about the best edge detection algorithms to implement in the code, as well as how to set up block diagrams and help minimize image noise. The MEMS setup looks something like this. And when the experiment is run, it moves to the side, a little bit like that. Now this movement is what we really want to control. So what we will be measuring is this region to the left with the two edges. They will change how far apart they are, but the distance should be somewhat controlled throughout the experiment. This is the front panel of the LabVIEW code, so this is what the user sees. When running the code, the user needs to select an image for the code to analyze, and while the code is running, you can change settings and draw a new region of interest if needed. The block diagram, aka the back of the code, is what actually makes the code work, so I'll be walking through that today. This region to the left defines our region of interest. So essentially, where are these edges that we are trying to find? The region of interest is defined in terms of pixel length. And on the image itself, it's represented as that green rectangle. So those are the inputs that I currently have set up. Now that we have our region of interest, let's introduce our image. The section here prompts the user to select an image from the drive, which I've mapped to be the user's C drive, and stores it temporarily in memory. This outside box is actually a while loop. As long as the code is running, the user can edit any of the parameters and the code will automatically update. This bit of code is part of the NI Vision module that is built into LabVIEW. It can find straight edges in a given image as long as all of the proper parameters are provided. And this section here are the parameters, namely edge option, search direction, and line options, although there are more. This is just an example from the documentation from this for what the different options are for the parameters, but I will be discussing parameter optimization later in this presentation. Once the straight edges are detected, this section overlays them onto the image for the user to actually see. Now, parameter optimization. Essentially, there are a bunch of different things that we can change that will change what kind of lines we detect, whether this is search direction, so whether we should search left to right, up and down, how strong the lines are, what angle they are. There's a bunch of different parameters, but I'll just be talking about a few. So for search direction, it does not appear to make a difference as long as the search direction is perpendicular to the line that we want. So whether we do left to right or right to left, still finds the lines that we need, which is expected. It just changes how the LabVIEW code actually processes the image. And by messing around with the search direction parameter, as well as the edge strength, which I'll talk about more later, the edge of the sticker on the MEMS device can be detected, but it seems very imprecise and changes the lines detected based on the search direction and is generally not recommended, although it is a possibility. The number of lines parameter seems somewhat self-explanatory. It's the number of lines that we want to find in our region of interest. However, no matter how many lines we request, there is a cap of how many lines can be found in the region of interest. As shown in the image to the right, although I requested 4 lines, we have only found 3 in the actual code. This implies that there is a certain hidden criteria for what constitutes a detectable line, even if straight edges fitting the description might be present in the image. This hidden criteria is minimum edge strength, also how present the line is in the image itself. I've found that a minimum edge strength of 54 to 56 is ideal for detecting both our left and our right edge. Above this value, the left edge fails to be detected. And below this value, as you can see, when I set it to 20, we find a lot more lines than we are interested in. It's mostly a factor when we're looking for more than one line, but even when we're not, the line that will show up if one line is asked for will be the most present line. So the one with what can tolerate the highest edge strength. Now, why do we care about parameter optimization at all? Why can't we just stick to the edge strength that I found and call it a day? Essentially, it's because it depends on our type of image. So we have bright field and dark field images. Bright field images are what we consider our classic images. Most of the stuff that we take in our everyday lives tends to be bright field. Dark field can be used with reflected surfaces, since the light reflection in bright field can be disadvantageous and mess with a lot of our data. The problem is when trying to put this into the code, even with messing with the parameters and edge strength, what happens is the right edge gets detected as 2 lines. So 2 lines, one on the left of the right edge, one on the right of the right edge, and then the left edge is eventually detected. So just to zoom in, that's what it resembles. The difficulty with this is that the priority does not seem to favor the left edge. And so what do I mean by this? I mean, as you can clearly see, there's 3 lines, and you might be like, Cynthia, why don't you just put 2 lines into your code? Why don't you ask for that? The problem is that then I only detect the right edge, which isn't very helpful if we're trying to find that distance between the left and the right edge. And with that, we can segue into future work and challenges. So currently in the process of optimizing the line detection code. So if we can't get the right edge and the left edge to display when I ask for 2 lines, what if we ask for 3? If the right edge displays as 2 lines, can we take that into account and maybe average it to find the middle of it, and then use that average to find the distance between the left and the right edges? Another thing to add to the code is to track pixel placement of the edges and export it as a data set. This has currently been giving me a bit of difficulty. I have been working on tracking the placement, but taking that LabVIEW of array and transforming it into a workable data format to find the distance between edges has been pretty difficult. In the future, we would also like to automate the import of images. Currently, when the code runs, it's set for the user to input an image. Ideally, we would want to hook this up to a camera and have real-time edge detection. Also, we would ideally like to compare these incoming images to the beginning state of the MEMS device. However, the way the code is set up, currently the images, when uploaded, are stored in memory temporarily and then deleted once the lines are detected. So having it save that beginning image might be a bit difficult. And in the long term, we would also like to connect this to a pico motor and have a PID loop to augment the MEMS device in real time based on the data that we're seeing. Some key learnings. First off, willingness to leave my comfort zone. I didn't start this project off with any prior LabVIEW experience. Most of my coding before this has been in MATLAB, which is not a block diagram language, so being willing to learn a completely new method of doing things has helped me grow and expand. Additionally, curiosity, I found, has always been an important quality to have in research, to be able to push the bounds and continuously learn and expand what we know. Most importantly, however, has been perseverance and continuing to work through difficulties. Even though I haven't been able to fully implement the code to the extent that I would like, there's been a lot of learning throughout the process, and it's given me a new sense of appreciation for research. Behind every successful experiment, there are dozens that didn't work as expected, but the important thing is to persevere and continue going. And with that, I would like to acknowledge the National Science Foundation for funding this research, as well as Edwait Gakwad, my mentor, and Dr. Pavan Kalaru, the PI. Additionally, I'd like to thank the TAMU O-REU team for coordinating the entire program and creating valuable experiences for everyone. It's been a blast. Thank you so much.